Welcome everybody. Sorry for the delay. We've had a few technical issues with the video. Hopefully we've sorted them out now, and we'll be able to get up and running. First of all, I'd like to share my screen with you. Okay. Michael, could you confirm that my screen is seen?
No, sir. Let me put you as the presenter.
Thank you.
Yeah, try it again. Yep, we can see your screen now.
Okay. Okay, sorry about that, everybody. Like I said, we've had a few technical difficulties, but we should be on track now. First of all, let me just introduce myself. My name is Paul Nock. I'm the segment manager for the motor rotating machine segment in Asia. A little bit about my background. I've been involved with testing electric motors in many different ways, literally all my working career, for various different companies and applying different type of test methods. Now, this technology that we were going to present, that we are presenting to you today, is brand new. It's for us anyway. There is a new standard that has come into being, supported by IEC, that enables you to reference your partial discharge results against this IEC standard. So the type of surge testing that we currently do when we're testing motor windings for shorts and turn breakdown of insulation is usually associated with like I said, with the word surge test, impulse test, that type of terminology. But what's new is during those surges or those capacitance releases from a tester pushing the voltage through into the motor, if there's any weakness in the insulation, any voids, there can be a discharge, which can also be detected. Now, this has become more and more used in industry, particularly in the motor design industry, if you like, the manufacturers and so forth. So what we're hoping to get through with this presentation today is a little bit of understanding of how that can help you in the field. What can help with testing motors statically for partial discharge, not while the motors are in operation. So what we'll do is we'll run through the presentation. The presentation is from a colleague of mine in the US. He'll go through it and he'll explain things along the way so that you can understand. But the capability is with our DX instrument, which is our Baker's, should we say, latest model of test equipment. And it enables us to maybe see things a little bit prior even to surge test failure. So at the moment, we use surge testing at a higher voltage than the supply voltage of the motor to look for early indications of the breakdown of insulation between the turns and coils. What partial discharge enables us to do is look that a little bit further and maybe get an even earlier idea of there's a potential problem going to happen. So with that, I'll ask Grace to start the video for the presentation. Grace, can you start the presentation, please?
Yes, hopefully you can all hear the audio. Because due to some technical issue, we cannot play the video from the GoToWebinar system. It's now playing from my laptop. Wait, please wait a moment.
All right, well, welcome everybody. Thanks for coming. Today we're going to be talking about the fundamentals of partial discharge, exciting relatively new technology in the reliability community. And so I'm happy to be able to at least give us an introduction basically to the idea of what partial discharge is and how we can use it
Grace,
further our
the
reliability.
video's not playing.
So just as a general overview to start, partial discharge is the localized.
Can you all hear the video and see the
Yeah.
screen?
Yes, sorry,
Yes.
sorry, Grace, I was on the wrong page. I apologise. Sorry, everybody. Please continue.
But can you hear it clearly?
Yes.
Yes,
Grace.
not too bad.
Okay, so we will play it this way then. Okay, thank you for confirmation then.
Electric breakdown produced between two regions of differing charge potential without a direct path between two conductors. It's a lot of words, but basically, really high voltage gets around some gases, they ionize, and then we get this this discharge, which isn't going from conductor to conductor, but just in a space, right, an ionized space where this discharge occurs. So it can happen on the external surfaces of insulators. It can happen internally in the voids of insulation. And so this is why in electrical motors and switchgear and transformers, especially where there's high voltage present, we're concerned about basically these little lightning strikes that can occur. As you can see in these beautiful pictures here, these discharges produce plasma, they ionize the air, produce volatile gases, not necessarily volatile, but corrosive gases, which can act to deteriorate our insulation systems, which certainly isn't desirable. Plus the heat that's generated locally as well isn't going to be good for our insulation systems. So again, under very high potential, these electric fields produce ions in the gases and in the surrounding the insulation materials. And when these potential differences are overcome, the breakdown occurs and that partial discharge happens. Now, typically this is in like I mentioned earlier, high voltage, greater than 5,500 volts AC, but can also happen in lower voltage situations, even in our 460 volt motors. If there's a high rate of change of voltage, so that DVDT, or the change in voltage with respect to time, happening very fast, can also cause these local ionizations to occur and have the same effects as the high voltage. So the resulting current flow produces plasma in the normal atmosphere, ozone, right? So ozone's a corrosive gas that actually acts to chemically attack the insulation, and it will cause that to degrade over time. So that's kind of an overview. Let's get into some more specifics and how PD can affect our equipment. So one of the casualties of partial discharge potentially is our cable systems. Specific XLPE type cables as an insulation that's known to undergo partial discharge deterioration under a process called water treating. And it has to do with the shape of the insulation degradation pattern. That's why they call it the water tree, the treeing. When cables are exposed to water, and then they have this a polarizing voltage around them, these discharges can lead to this type of deterioration that you see here in the photographs. We can see the presence of partial discharge damage, and this phenomenon definitely occurs in high voltage switchgear. Again, typically in that 6,000 volts or above, 13.8, even in the higher voltage switchgear as well. Corona can occur in the switchgear components, but it can also be observed in our motor junction boxes, so it's close to our motors in these high voltage systems as well. And you can see these kind of unique, the powdery discharge is a pretty common visual cue that you have corona. It could be, there's white discharges and there's black discharges. I've seen both. Another observation that you might experience is the smell of corona, right? The smell that's produced during active partial discharge. So if you're in a room with a high voltage motor or high voltage switchgear that has corona activity going on, you can literally smell the ozone in the air. Okay. In the motors, right? So high voltage motors, as I mentioned, 6,000 volt motors typically and above. You can see these types of evidences. Again, that's that powdery deterioration of the external surfaces of the insulation is the most common visual representation of corona activity that can happen As we see here, these are the coils. On the right here is the exit, the iron core slot. That's a pretty common place, as there's a large gradient of voltage difference in potential from the ground plane to the high voltage coil. In between conductors, here we see as the coil exits the slot again, and the coil makes a bend there potentially between phases. Right there is where we have some high voltage activity and partial discharge evidence in the coil. This one in the upper right is from a traction motor that was operated on a VFD in a transit system, I believe in South Korea, and the partial discharge eventually blew out the insulation, and the motor ended up failing at the ground plane there at the edge of the iron core as well. So yeah, between leads, between power cables, cables in the motor junction box, that's why it's so important for high voltage motors to keep the leads separated from one another. There's certain distance and spacing requirements that we try to maintain in the design of the motor winding itself, and as well as the cables internal to the junction box, to prevent a lot of what we're seeing here. And then sharp points or connections. I don't have a good picture right now of the coils. When we make the connections up, they're usually done in a loop fashion versus a fixed point where the ionization can kind of collect around that point and produce partial discharge. Okay, so not only external to the windings, but also internal to the windings. And when voids are present in the internal insulation system, those little pockets of gas are prone to the ionization and subsequent discharge or partial discharge. And then if those partial discharges occur internally, we'll have the same effects, right? We have the production of corrosive gases, potential for plasma and heating of the insulation, and then over time that's going to degrade the insulation internally. Obviously, that's not desirable for a reliable insulation system. The lower note here, I have a picture of a VFD voltage current waveform. But even in low voltage motors, where we have this rapid change in voltage with respect to time due to the nature of the IGBT switching circuits, that rapid change in voltage can cause local ionization as well. So we're not only concerned with discharge in high voltage motors, but we're also worried about partial discharge occurring in low voltage motors that don't have adequate varnish treatment processes and potential voids internal to the motors. So this probability failure curve, bathtub curve, we're probably all pretty familiar with this as reliability professionals, but partial discharge is helping us in a couple of different places. On the left side here in the infant mortality phase, where we have a high probability of failure due to manufacturing defects or installation problems. In the case of partial discharge, again, we're looking from a quality perspective for the evidence of partial discharge that occurs in voids or potentially on the external surfaces of high voltage motors. So if we have some kind of design flaw or some kind of manufacturing flaw, partial discharge detection is very important in that phase of its life. And then once we've gotten through that phase, we understand that the probability of failure is low because we have a high quality product. Then we want to look at it over time to see that potential voids are being created because of movement of coils or other internal deterioration of the insulation. That if partial discharge activity starts to increase at lower and lower voltages, that would be an indication that we're at least accelerating our degradation and possibly entering an end-of-life condition. So I'll show you later how partial discharge may be a little more predictive than maybe even surge testing is at lower voltages. All right, so detecting partial discharge. There's two primary schools of detection when it comes to primary discharge. That's online detection and offline detection. And online, as the name would suggest, is performed when the equipment is energized and in operation while the equipment is online. Detection occurs at the nominal voltage that the motor is typically operating at. So we're not testing to elevated voltages that the windings might see during transient conditions, but we're testing at the nominal level. So when partial discharge activity starts to increase in the nominal level, it's definitely something that we want to act upon right away. It typically requires some type of coupling device attached to the motor terminals, some kind of capacitor or some kind of high frequency CT that picks up the partial discharge activity, as I'll show you a little later. It occurs in the high frequency band, typically in the kind of the radio frequency band. So it does require some kind of special equipment that's permanently installed and continuously monitored. So the other method that I'm going to primarily focus on today, because that's what my company produces, right, is some offline equipment, is what we call PD on surge, where we leverage the impulse, the high voltage, the rapidly changing voltage, steep fronted surge pulse, and we leverage that as a partial discharge inducer, if you will. So it's performed while the equipment is de-energized offline. The detection occurs at the higher voltages where the PD induction is more likely to occur. So during transient conditions, again, during these rapid changes in voltage on low voltage motors with VFDs, we're simulating those transient events and seeing if partial discharge is occurring in certain portions of the winding. This offline method, there's a bunch of different detection methods. I'll talk about what we do, and I'll show you a couple of the other methods that are available as well. So one of the methods is acoustic. You can literally hear partial discharge occurring, especially when it's external and on the surfaces of the insulation systems. But so we basically just use a sensitive microphone to kind of pick up those high frequency emissions as one detection method. Radio frequency, where we'll take an antenna that you hold in your hand, and then you can kind of sweep the surfaces of the insulation system to kind of determine where partial discharge might be occurring. The acoustic and radio frequency methods are really good for isolating locality, right? So we want to know where partial discharge is occurring specifically in a system. Those methods might be better suited for location tracking kind of detection. As I mentioned, during online testing, high frequency current transformers can be used to convert that high frequency waveform, that partial discharge component, into measurable voltage signals for detection. Capacitive coupling. So we basically take a capacitor and we allow that capacitor with a high frequency bandpass to kind of allow the high frequency stuff to get through and for detection. That's one method. And then finally, the resistive division method, where we're basically using a voltage divider in the form of a bunch of resistors chained together to reduce the voltage or attenuate the voltage. And then we use some high frequency filtering methods to again to isolate the specific frequency of interest and quantify the peaks of those high frequency discharges, those partial discharges. And this is the method that we use in our MEGGER DX surge tester. And so a really great analogy for understanding exactly what partial discharge is the idea of lightning strikes in the sky. And specifically, a full discharge would be a lightning strike from, say, an ionized cloud to Earth, right? Or, the actual flow might be reversed there. But if we have cloud-to-cloud discharge, though, where there's a significant difference in potential between, say, two clouds and a discharge occurs, that would be in the space, right? In the space of the air, in the atmosphere. It's not between two conductors, but two regions of differing potential. And that's basically what happens inside those motors where those voids occur. We basically get a cloud-to-cloud kind of discharge. And if you've ever heard of, if you're young, maybe you haven't even heard of AM radio, but for those of us that have the pleasure of listening to AM radio while they're driving in the car during a thunderstorm, you might have heard those static pulses that occur when lightning strikes. So I'm playing some audio now that's representative of those discharges, and basically the AM radio is picking up those lightning strikes and the EM pulses that are being emitted by those lightning strikes, and you hear that audible detection, right? So basically, we're doing the same thing as the AM radio, right? We're detecting those high frequency pulses and we're isolating those, and then we're kind of quantify the peaks relative to some threshold so that we know that partial discharge activity is occurring in our motor or in our system that we're testing. If you couldn't hear the audio, you can come back. Again, I think they're going to send the video out tomorrow. You'll definitely be able to hear the audio tomorrow. All right, let's move on. Okay, so partial discharge can occur over very large bandwidth, but primarily we're talking about the radio frequency kind of bandwidth, the high frequency bandwidth, somewhere between 20 megahertz and up to maybe as high as 3 gigahertz. And so just as a comparison of frequency, and those of you that are familiar with surge testing, and since we're leveraging the surge pulse frequency ranges somewhere between 500 hertz to 200 kilohertz, depending on circuit characteristics of inductance and capacitance. So we're talking about a much, much higher frequency band than what we would normally see in the surge wave. So again, we're leveraging this fast rise time on the left here of this surge wave. This is where this is that rapid change in voltage that's causing local ionization to occur. If it is going to occur, that's what's going to prompt that. And the high frequency discharges, if they were displayed on here, and the voltage is so small, typically in the millivolts with our resistive divider network, we wouldn't see it normally riding on the surge pulse. If the partial discharge is very large in amplitude, it is possible to see maybe some riders there. But we use special, again, filters and processing equipment to isolate those high frequency regions of the waveform. Now remember that when the surge pulse rings back and forth through your winding and back into the capacitor of the tester, we create this nonlinear distribution of voltage across our coil system. So again, this nonlinear distribution means that the voltage and the effect of that steep fronted rise is primarily going to act upon the early windings. So if we are seeing partial discharge, it's most likely either in the leads, the connections, or the first few coils of the winding circuit. And we're not going to find partial discharge in the deepest part of the winding, unless, of course, as a motor manufacturer, as a motor shop, or even if as a motor owner, if you have the ability to break the circuit apart into its constituent phases or even groups, depending on the number of leads that we have in the junction box, we could do some surge testing back and forth to get deeper parts of the winding tested for partial discharge, primarily from a quality perspective, as this is typically not practical to perform in the field when the motor's installed, in its normal operational configuration. Okay, so again, we're just taking the high frequency bits. Here on the right, you see an oscilloscope view of a couple waveforms. One would be the normal view of the surge steep fronted rise, and then the trailing attenuated ringing wave pattern. And here we see this rider, this high frequency rider here on one signal that's been specially tuned to be able to see that high frequency bit. And we're basically taking that high frequency bit and we're extracting it from so it's no longer riding this larger low frequency wave and placing it on its own axis. And again, this other axis we see on the right here is in millivolts. PD voltage is a millivolt signal riding on 1,000, multiple 1,000 volt surge signal. So it's important that we have two axes so that we can evaluate the surge waveform as well as the high frequency rider that's created from partial discharge. Okay. So the partial discharge event we see are these peaks of that high frequency component. Of course, this is a graphical representation of what I just showed you, but these peaks that exceed a known threshold, or not a known threshold, but a set threshold that we define above the noise level. So we want to make sure our threshold's well above the noise. And then when the PD occurs, it'll break through that threshold. And we call each one of these peaks that breaks through, each one of those is considered what we call a partial discharge event. And the events count if they're positive, and they count if they're negative. Sometimes I've shown these both positive and negative on either side, but it's not always the case. Sometimes we'll just have a single peak that goes up, or maybe even a single peak that goes down. Each one of those would also qualify as a partial discharge event. And then what we call a partial discharge pulse would be a surge pulse that contains more than a selected number of PD events. So this is a means of kind of isolating PD while mitigating any noise, right? We want to make sure we have a certain number of events so that just one random pulse isn't going to set off all kinds of flags and alarms for us, right? We want to see a significant amount of these events occur. Typically somewhere in the neighborhood of 3 to 5 events would be sufficient to rule out the idea of noise that's going to penetrate our threshold. Of course, we have to make sure we set our threshold properly to begin with. Okay, so the MEGGER PD detector, let's see, determines the moment at which PD activity begins and records that voltage, what we call partial discharge inception voltage, the voltage at which we have the right number of events, exceeding that threshold. So it's really a go, no go detector, right? It's like, do we have PD or do we not have PD? And at the point where we have PD, as we're increasing our surge voltage, we're going to get to a point where the PD indicator is going to say, yep, we have PD, and then we're going to record that voltage in what we call PDIV, or partial discharge inception voltage. Once more than half of our surge pulses are partial discharge waves, then we say we have repetitive partial discharge inception voltage. So that's where basically not only do we have PD, but PD is consistently happening through the majority of all of our surge pulses. And then one thing that's unique about doing surge testing while we're looking at PD is that not only do we want to know where partial discharge starts to occur, we also want to know when it goes away. So we'll actually get to our test voltage, and then we'll turn the surge test around, and then we'll ramp the voltage down until the partial discharge activity ceases. Now, typically, this is a voltage that's it's going to be a little bit lower voltage than where it may have started, because once the activity begins, right, ionization is present, it's a happy environment, right? It's more readily going to occur. So it's not uncommon to have a repetitive extinction voltage that's lower than the voltage at which partial discharge was initiated. Okay. Now this is what we call a house plot, and this is a common way of displaying the partial discharge activity that occurs throughout the entirety of the test. And we don't have a whole lot of time. I can't get into a lot of the specifics of how to analyze this. Basically, the lines represent the voltage, the surge voltage, the peak high surge voltage with its axis, y-axis on the left here, and then the dots represent partial discharge events. And remember, PD events are where the partial discharge high frequency poke through the threshold. So all of our voltages up here are recorded for each phase, so we can isolate if we have partial discharge in one particular phase, at what voltage, again, it starts, repetitive, and then to distinguish itself from a repetitive standpoint, and then completely at the end of the test. Okay, so again, we have detection thresholds, millivolt readings. There's a lot of different settings, but basically, I want to make sure we understand that from our perspective, when we're just looking for partial discharge activity, we're really doing this kind of go, no-go detection. It's simply stating that the voltage, this is the voltage at which partial discharge activity is present in our winding. And when it goes away, there's nothing more. We're not evaluating the energy level that's consumed by the partial discharge. While that information might be helpful in some regards, primarily in design and trying to mitigate partial discharge, for most of us, from a reliability professional standpoint, we don't really care much about that. We just want to know, do I have PD or don't I? And if I do, then I can take some actions to improve the quality of my services, or improve the quality of my vendor, my OEM supplier for my motors, or perhaps my installation practices and my switchgear, my cables, or all the different things that can cause PD. So again, we don't quantify the energy present. Some equipment does, but that's why we represent our partial discharge signal in millivolts, not so much in the microcoulombs of energy that you might see some other equipment display. Okay, and just a brief glimpse into the guts of the tester, where we do, we can in the settings adjust the threshold levels, adjust the events, and the detection system sensitivity is there for as a reference to noise levels. So again, we understand kind of at the time of test where the noise levels were. Yeah, we've covered all those things. So just a couple things to keep in mind if you are, doing partial discharge testing. We run into some issues where, depending on the voltage level which you're testing, when you're testing the higher voltage levels, say if you're looking for PD in a 6,000 volt motor or even a 4160 volt motor, once you get around that 10,000 volt test threshold, having the leads laying on the ground, not a good idea. You'll get partial discharge potentially from the test leads themselves to the earth. So we want to keep those isolated from the ground plane. We'd also want to make sure that the leads are separated from one another. If I'm surge pulsing down lead 1, the lead 2 is sitting next to it. Lead 2 is at a ground potential, so there's a high difference in potential and potential for partial discharge to occur there as well, and give us false indications, right? That's what I'm trying to get you to avoid. You don't want to think you have something going on in your motor when it's just the test lead configuration that might be causing some of the issues. As I mentioned earlier, we want to adjust those millivolt thresholds to compensate for high noise environments. So we need to first, before we even do any testing, evaluate where the noise threshold is for our particular location, set those thresholds accordingly, and then go ahead and do our surge test and evaluate the partial discharge during surge. Keep in mind that when we do partial discharge testing, this high frequency stuff doesn't travel far, right? It's attenuated rather quickly, much in the same way the high frequency vibration is attenuated fairly quickly through its medium. So we need to test really close to the winding. We can't get away with testing from the switchgear to look for partial discharge in the motor coil, for example. Got to get into that junction box, break those leads, and test locally. So that is a little bit of a little more cumbersome than our normal surge testing from the switchgear would entail. Okay, so real quickly, I'm going to go through just a quick case study, and then we'll be able to open it up for some questions. We got some time here. This particular case study comes to us from Professor Sungbin Lee from Korea University, and this is a partial discharge case at a HVAC motor manufacturer in South Korea. And so here you see a picture of the winding, and in this particular, it's a random wound motor, pretty common design. This particular winding that we're looking at here is copper, but they decided for some cost reduction reasons, right, and try to make a lower cost product, to go to aluminum. And a lot of you are probably thinking, that doesn't sound like a great idea. But anyway, they went with that method because they were going to get a 15 to 20% cost reduction, and so for some financial reasons there, and they were going to increase their profit, I'm sure. But what happened when they did that? Their failure rate increased by 10 times. Big shocker there. So it probably didn't work out as far as the cost reduction as much as they had hoped. Looks like a 40-month period where we were seeing these increased failure rates. The failure location was on the terminal end of the insulation. It had passed complex corrosion, salt spray, high temperature and humidity, pressure curtain, thermal shock, accelerated aging test, but it was also passing IR, which is insulation resistance test, DC high pot test, surge, and even pinhole QC test of the actual conductors that were used to make the coils. So all these tests are passing. It's passing all their QC, and yet these motors are going out into the field, and within just a few years, they're getting a much higher failure rate than they were before they had made the change. So they go back, they say, what do we change? Okay, now we're doing aluminum. Now our failure rate's increased. What's causing the problem? None of our QC stuff can see it. What can we do? So insulation failure was observed, again, as they mentioned, on the terminal end of the winding. Turn phase insulation failure due to partial discharge was suspected. Suspected root cause was the frequent starts and stops in the hostile environments, being outdoors of these HV AC, I believe, condenser motors. The degradation in turn and phase insulation due to PD activity was suspected, either due to high ductility of the aluminum, which has about, I guess, 70% higher ductility than copper, and also high thermal expansion coefficient of the aluminum. So the growth basically of that coil, the growth and shrinking of that coil also was much more rapid than copper. Comparative PD on surge testing was performed of all the copper and aluminum winding coil samples for verification. So this is the results of their data. So this is just an Excel graph that kind of displays kind of a percentage of threshold. That's what we're looking at here. So the measurement of PDIV, if you remember, PDIV stands for partial discharge inception voltage. The number of PD pulses measured at fixed voltage. You can see comparatively from the copper crimping to the aluminum crimps design. The aluminum crimp design had much higher partial discharge activity, significantly higher than that of copper. Partial discharge surge test is capable of screening out the samples with high risk of failure. So they were able to, if they wanted as a quality test to say, oh, nope, these coils have some issues because of, probably because of void formation. And as it turned out, because of the ductility of the aluminum and the bend radiuses, they were actually creating pockets of voids in the bends where the varnish treatment wasn't adhering properly because of the increased ductility of the aluminum coils. So the accelerated aging of individual samples to compare PDIV before and after aging. So just looking from a quality perspective, again, the other tests weren't showing anything under aging tests and high stress environment testing, but we wanted to see, does partial discharge show an increase before and after aging? So this would be, the first thing is kind of more of a quality QA initial testing, and this would be, as the insulation ages, does partial discharge show any changes over time? And so you can see the normal operation temperature ranges in the hours of aging that was either simulated or conducted. I'm not sure, but they did all that stuff in temperature controlled ovens and whatnot. And here you can see that the before and after of the aluminum samples comparatively. And this is a little misleading, the graphs. While the before aging looks higher than the after aging, realize that this top scale, that's 180 events, is actually about halfway here on this graph. So the number of events significantly increased on all the samples as aging occurred in this winding. So we saw a significant decrease in the partial discharge inception voltage. So with aging, the voltage at which partial discharge activity begins decreases over time. But the number of samples with low PDIV can be screened out with the PD surge test, and the values of the events increased aging cycle as well. So let's see. So kind of going back to our partial discharge quality reliability, there's basically two zones where PD activity can help us out: at the QA at the beginning and infant mortality, and then also at the end of life, right, as a reliability tool to evaluate we're reaching those last stages as kind of a predictive indicator that we're getting to a point where the motor winding might fail. All right, so I think that might be it. Yep, that's it. So we're here at the question phase. I'll open it up to Paige to kind of lead us through that process.
All right, perfect. Thanks so much, Drew. So like Drew said, guys, we're going to open it up for the Q&A session. So if you have any questions, go ahead and enter them now in the question panel of your GoToWebinar screen and submit them for Drew to answer. Again, just as a quick reminder, your questions will be answered and read anonymously, so no need to worry about getting called out. And if we run out of time here and don't make it to your question, Drew will be sure to reach out to you after the webinar is finished here today to make sure that your questions have been answered. All right, Drew, so to get us started, our first question up here asks, does performing this partial discharge with surge testing harm my motor winding?
Yeah, that's a great question. And We've answered this in some high voltage webinars in the past, but of course, surge testing in and of itself is testing much higher than the nominal voltage, and so it's a common, perfectly legitimate question to say, why would I be wanting to test my, say, 460 volt motor at 2000 volts just to see if there's partial discharge when it's only rated for 460 volts? And so the common misconception there is that because the motor is rated for 460, that the insulation system is rated for 460, and that's not the case at all. The insulation system is actually rated for breakdown voltage, and a 460 volt winding at the beginning of its life has a breakdown voltage of about 28,000 volts to ground. So our testing at 2000 volts isn't even scratching the surface of what the insulation is capable of holding back. And of course, if your winding isn't capable of holding 2000 volts back, especially at the beginning of its life, then there's probably some significant quality defects that you want to identify as a problem. So doing the partial discharge evaluation is just, kind of riding on the fact that we're doing a surge test anyway, and now we're just seeing, is there partial discharge activity, which would indicate the presence of a void in the insulation system itself, which again doesn't mean the motor isn't going to be operational today, but it means it's probably going to be less than reliable for the long term, and it's not the best reliable or highest quality motor that we can have.
Okay, now that's the end of the video. So it now comes to our Q&A session. If you have any questions, please feel free to type in the question panels, and we'll answer your questions.
Hi, Paul. We have a question here.
Okay.
One question is the cable skin effect included in the PD?
Sorry, could you say that more clear again, Michael?
Yep. Is the cable skin effect included in the PD?
No. So when we use the PD with surge, we don't go through the cables to the supply of the motor. We really want to just measure what partial discharges are happening inside the motor insulation. So it's a motor insulation tester. So in the case of testing a motor in the field, we would have to go to the terminals at the motor, or if it was a rewind shop or a repair shop or one in the stores or being serviced, we would use it at the terminals at the motor. The cable can upset the readings, and it just makes it so much more complicated to be testing through the supply cables to the motor, because then we don't know really where the discharges are occurring. If we test at the motor terminals, then we know for sure that the internal discharges on the motor are actually in the windings of the motor and not at a junction on the cable or in the contact. So many different things. So it's very important that we take the readings at the motor terminals. Unlike surge, for example, a normal surge test that we would do in the field, we could do from the panel. But with PD, to get accurate readings that are trendable, we need to be able to take the readings at the terminal box.
Yep. Or maybe it's trying to say or to mean about the skin effect is the eddy current loss. So I don't think we measure that in our PD, the eddy current loss.
No.
So another question here for in general, what is the percentage confidence of PD test for motor?
Well, the confidence for this type. Remember, there are several different types of partial discharge testing. There's online. There's antenna style partial discharge. Well, the good thing about this type of partial discharge testing is we test through the motor terminals with hard connections. So we haven't got to worry about having an antenna set up type of data collection that we have to get in exactly the same place every time to be able to trend the results. Remember that partial discharge of any kind is not a pass-fail criteria. It's generally a trending tool. So what we don't want to see is the readings change in any way from maybe let's just say when we first start doing the testing, we've already done our ground insulation testing, our resistance testing, our surge testing through the coils and turns, and then when we do partial discharge on surge, then it's also going to give us that early levels of discharge that is occurring on that winding. But what we do is we take the inception voltage, the repetitive inception voltage, the discharge voltage, etc., and we kind of make a house plot, and we measure the activity within that plot. But what we don't want to see is the inception voltage becoming lower and lower and lower. We really want to see that inception voltage for partial discharge as we increase the voltage as it goes up from 10 volts, 100 volts, 150, 200 volts, etc. We want to see that when partial discharge occurs, it is occurring at approximately the same voltage of inception and discharge all the way through the motor's life, and then we know it's not deteriorating. But as soon as that inception voltage starts to drop, then we know that we're starting to see more and more discharges at a lower voltage, which could indicate that the insulation is beginning to weaken. So that's when we use the trending side of partial discharge to make our conclusions. But there is no pass-fail criteria for any partial discharge. It's all in the trending, if you like. So we're looking for change, and a negative change, obviously.
Right, very well said, Paul. Actually, I have a questions. What are the products that we have this partial discharge?
Yep.
Our static.
Yeah.
Yeah.
So it's our static DX range. The DX is our it is a very flexible instrument. We can also do high pot, surge, partial discharge, of course. We can also do rotor testing. We can do step voltage, insulation resistance, low resistance joints through Kelvin connection, polarization index. We can do coil-to-coil comparison, armature testing. It's really quite a flexible machine, and with the added combination of the different partial discharge on surge, makes it a very all-round powerful tool to be able to really identify at an early stage any particular insulation issues with any electric motors.
Right. Thank you so much, Paul, for the answer. So, guys, I guess that's all the questions that we have. And again, we apologize for the technical issues we had. So, again, to all, thank you so much for attending this webinar. Please have a good day and stay safe. Thank you, Paul, and thank you, Grace.
Thanks, everybody. Bye.
Bye.
Thank you, everyone. Bye-bye.